Hey guys, my name is IBM, and today I would like to solve the October-November 2024 multiple choice questions. This is paper 1 multiple choice. This is going to be paper 1-1. Do not forget to visit our website, which is just growing, www.cieresourcemaster.com, where you can download the papers. You can find their resources, especially those of physics are already there. Other resources will be coming with time, but for now, most of the physics resources for both IGCSE, AS, and A levels are present. Um, on that website, you'll also find this same paper, but with the answers written, and you can download it. Unfortunately, it won't be free. It will just be around $5 with the answers written on it. But if you want to just watch the solutions, you can just watch on YouTube for free. Okay, so I'll not go through the instructions, they are the usual instructions. I'll not go through the data, I'll just go straight to question number 1. What are the SI base units for the moment of a force? Of course, we know that moment of a force, I normally use tau because moment is the same as torque. The moment of a force is the product of the force and the perpendicular distance of the force from the pivot. That is the moment of the force. The base units for force are actually kilogram meters per second squared, because we know that force is equal to mass times acceleration, and mass is measured in kilograms, acceleration is measured in meters per second squared. And the base units for the distance will be the meters. So the units for the moment or the torque is going to be the kilogram meters per second squared multiplied by meters, which then simplifies to kilogram meters squared per second squared. So this is going to be our answer to this question, and this makes D to be the answer. Okay, so which statement about vector quantities is correct? Of course, we know that vector quantities have both size or magnitude and direction. Vector quantities have both size or magnitude and direction, so we look for size and magnitude. So acceleration of free fall is a vector quantity, which is true because it has a constant magnitude. A constant magnitude is not enough to tell that a quantity is a vector quantity, so this is not true. Temperature in degrees Celsius is a vector quantity. Temperature itself is a scalar quantity. We can't tell the direction, so that statement is wrong. Time is a vector quantity. Time itself is not a vector quantity. We can't tell the direction, so that's wrong. Weight is a vector quantity. Weight is a force, and a force is a vector quantity because it has a magnitude and direction. So weight is a vector quantity because it has direction. So this makes it a vector quantity. So the answer is going to be D. Density of the material of a rectangular block is determined by measuring the mass and the linear dimensions of the block. The list shows the results obtained together with their uncertainties. So the quantity is density. So these are the quantities given: mass, length, width, and height. The density is calculated to be 2.5 grams per centimeter cubed. What's the uncertainty in this result? Because the density is already calculated, I will not calculate the density again, but it is calculated from the formula density equals to the mass divided by the volume. Since they gave us the dimensions, they gave us length, width, and height, so density is going to be the mass divided by the volume, which is length times width times height. So because of division and multiplication, I will just sum up the fraction uncertainties. Therefore, the fraction uncertainty in the density is going to be the same as the fraction uncertainty in the mass plus the fraction uncertainty in L plus the fraction uncertainty in W, that is the width, plus the fraction uncertainty in the height. So it means the fraction uncertainty in the density divided by the value of the density, which is 2.50, should be equal to For m, that is 0.1 divided by 25.0 plus. For l, that is 0.01 divided by 5.00 plus. For w, which is 0.01 divided by 2.00, then final plus 0.001 divided by 1.00. So this is the sum of the fractional uncertainties. I'll just check with my calculator. So I'll just say 0.1 divided by 25 plus 0.01 divided by 5 plus 0.01 divided by 2 plus 0.01 divided by 1. I didn't change the units because the density is given in grams per centimeters cubed, and the other quantities, the dimensions are also in centimeters, so it wasn't necessary. So this is giving me that fraction as 21 over 1000. So I'll just make the fraction uncertainty in the density is the same as 21 over 1000. So I'll just cross multiply. So the absolute uncertainty in density is going to be equal to 21 divided by 1000 times 2.50. So that is just times 2.50. So that is 21 divided by 400, which simplifies to 0.0525. So this is 0.0525. So uncertainties are good enough to one significant figure. Of course, this one is grams per centimeters cubed. So to one significant figure, this is 0.05, which makes the answer to be C. What is the reasonable estimate of the volume of one page from the examination paper? Volume of one page from the examination paper. So we are going to make several estimates here to arrive at the correct volume. Number one, if we try to estimate the width, we're going to start by estimating the width of a question paper. Since you have a question paper on your table, you notice that the question paper has a width slightly longer than your set ruler, which is about 15 centimeters. So the width is going to be approximately, I'll just take approximately 20 centimeters. You can check with your calculator. So the width is approximately 20 centimeters. When you check with your ruler, because you always have a question paper on your table, the width is approximately 20 centimeters, which is 2000. I think that is 20 centimeters. That is 200 millimeters. Then the length of a paper is more than the 30 centimeter. Is about the 30 centimeter ruler. So I'll estimate the length of the paper to be approximately 30 centimeters, which is approximately 300 millimeters. Now, an examination paper could have approximately, I think the normal page could have about 20 pages. I mean, the normal exam may be around 20 papers. If you try to check your usual paper, paper one has almost 15 to 16 pages, which are normally 4 papers, but some examination papers can be really heavy, so they could be around 10 to 20 pages. But even if you don't do that, you may leave the thickness of a page to be, I'll leave the thickness unknown, and I'll just use reverse. I'll check these volumes in the opposite direction. So let's say the thickness is not known, and know that the volume is given by length times width times the thickness. So the volume should be equal to 200 times 300 times the thickness. So we are going to check which of these ones gives a reasonable thickness for one page of the paper. The volume which gives a reasonable thickness for one page of the paper is the correct volume. So we check. We can start with this one. Which thickness does this one give? Where there is V in this equation, I'll just put that volume and check what T is. So this one is going to give us, let's say, what is the value of T for this? I'll just check my calculator. So this is 60 divided by 2, the other one was 200 millimeters times 300, which is, so this is giving an extremely small thickness, that is 1 times 10 to the power of minus 3 millimeters. That is too small, so this is going to be out. Then I'll check B. What is the thickness given by B? I'll just press my calculator. So we have 600 again, divide by 600 divided by 200 times 300. So this is giving us 0.01 millimeters, 0.01 millimeters. That is also still very small. So this can't be a thickness of 1 mil. A paper cannot be cannot be a thickness of 0.01 millimeter. That is too small. So let's check C. C, the thickness, the volume is 6,000. Then we divide by the dimensions, 200 times 300. So this is giving us a thickness of 0.1 millimeter. I think this is a reasonable thickness, 0.1 millimeters. In 1 millimeter of a paper, there could be 10 papers fitting in 1 millimeter. If you look at a ruler and you try to put there 10 papers, you notice that the thickness of 10 papers may be approximately 1 millimeter, which means one paper could be approximately 1 divided by 10, which is approximately 0.1 millimeters. So this one is giving a reasonable estimate for the thickness of a paper, which means the answer is most likely going to be C. We can check D and see what thickness it gives. So from the calculator, the volume is 60,000, then divide by 200 times 300. I think this gives us 1. So this one gives you a thickness of 1 millimeter. 1 millimeter is really very big. 0.1 centimeters cannot be the thickness of a question of the page of an examination paper. So this is really very big. So this means this is also wrong. So the answer is going to remain C. I used just back substitution to check and see if the thickness given by the volumes which are stated is reasonable. An object is projected from horizontal ground at a velocity of magnitude u and angle theta to the horizon. It hits the ground at time t after it is projected. Assume air resistance is negligible. Whenever air resistance is negligible, then the acceleration is going to be g, which is 9.81, and it will be constant. The equations of motion can also therefore apply. Which statement does not describe the motion of this object? Does not. Let's first resolve this velocity. So resolving it to the horizontal, this is going to be u cos of theta. Resolving the velocity to the vertical, it will be u sine of theta. So the horizontal component of the object's velocity is constant and has a value u cos theta. I think that is true. The horizontal velocity remains constant because acceleration in the horizontal is always 0, because the resultant force in the horizontal is 0. No force acts on the body in the horizontal. The only force acting is in the vertical, which is the force due to gravity. So this statement is correct. The horizontal distance traveled by the object is t times u cos theta. Let's check the horizontal distance. The horizontal distance is going to be s. I will get it from s equals to ut plus a half at squared. where s is going to be the horizontal distance. Initial velocity in the horizontal is u cos theta, but acceleration in the horizontal is 0. So this is going to be equal to u cos theta, then multiply this by t plus, because the acceleration in the horizontal is 0, this other part will be 0. So the horizontal distance is u cos theta times t, which makes this one correct. So this is also true. Time taken for the object to reach maximum height is t over 2. The time to reach maximum height is t over 2. In other words, they said it hits the ground at time t after it is projected. So let's first find what t is. Of course, to find t is the total time. So s equals to ut plus a half at squared. So if it goes upwards and comes back to the same horizontal ground, s will be 0. The vertical displacement is 0. That is, s in the vertical will be 0. Because we are considering vertical motion, initial velocity, because maximum height is in the vertical, so initial velocity in the vertical is u sine of theta, then multiply this by t. Because to went against gravity, acceleration a is going to be equal to negative g, so this will be minus a half times g, then t squared. So one t cancels, and when I make the remaining t the subject, it means that t is going to be equal to twice u sine of theta divided by g. That is the total time to reach the maximum height. Then what is the time? That is the total time for the whole journey. So small letter t, time to hit the ground, is 2u sine theta divided by g. What is the time to reach maximum height? Time to reach maximum height, I will use v equals to u plus at. At maximum height, v is 0. Initial velocity in the vertical is u sine theta. Because it moved against gravity, this is going to be minus g times t, because the acceleration in the vertical is g. Now this t is, I'm going to call this t capital T to distinguish it from the first t. So this is going to be capital T. So capital T is going to be u sine of theta divided by g. So when you compare capital T and the other t, you notice that the time, when I multiply capital T by 2, I get the other one. So, you can try to divide the two equations. You can try to divide t over small t. This is going to be u sine theta over g, then divide by 2u sine theta over g, which is going to be equal to 1 over 2. So it is going to be 1 over 2. So t over small t equals to 1 over 2, which means that capital T equals to small t over 2. So this statement is also correct. So that means the answer is going to be D. The vertical component of the object's velocity is constant. The vertical component is constant. It is not constant. It decreases to 0 at the highest point and has the value u sine theta. This part is correct, but the first part is not correct. The vertical component changes because there's an acceleration in the vertical, so this is not correct. So it's not constant. This part is what makes this not true. So the answer is going to be D. A person traveling on a motorway a total distance of 200 kilometers travels the first 90 kilometers at an average speed of 80 kilometers per hour. Which average speed must be obtained for the rest of the journey if the person is to reach the destination in a total time of 2 hours and 0 minutes? So I'll first find the time taken for the first journey. I'll call it T1. T1 is going, of course, time is the distance divided by the speed. So the distance for the first journey, 90 kilometers, divided by the speed, which is 80 kilometers per hour. So the time here is going to be 9/8 hours. Okay. Then the second journey, it means the time for the second journey, I'm going to call it T2. T2 is going to be 2 hours minus T1. So it's going to be 2 minus 9/8. And I think 2 minus 9/8 must be 7. That is 16 minus 9. That is 7/8 hours. So that is the time for the second journey. Then the distance for the second journey, I will call it D2, is going to be 200 minus 90, which is 110 kilometers. Therefore, I can now find the average speed, because speed is equal to distance, so it will be D2 over T2. So D2 is 110 kilometers divided by T2, which is 7/8 hours. So I'll just check my calculator. 110 divided by 7/8. So that's 125.7. So the speed here is 125.7 kilometers per hour. So 125.7, this is approximately 126 kilometers per hour. So the answer is D. A car of mass 1,200 kilograms has momentum 18,000 kilogram meters per second. What is the kinetic energy of the car? So we know, of course, we know the equation which relates kinetic energy to momentum. If you don't know that equation, you can just combine momentum. We know that momentum equals to mass times velocity. And we also know that kinetic energy equals to a half mv squared. So when you combine the two equations, you'll have an equation that kinetic energy equals to momentum squared divided by 2m. So I'm just going to substitute in this equation. So momentum is 18,000, but should be squared, divided by 2 times the mass, which is 1200. I'll check my calculator. 18,000 squared divided by 2 times 1200. So that's 135,000 joules. And 135,000 joules is the same as 135 kilojoules. So the answer is C. A ladder is positioned on icy frictionless ground and is leaned against a rough wall. At the instant of release, it begins to slide. So the ground is smooth, no friction. The wall is rough, there is friction. Okay. So if the ground is smooth, the only force acting on the ground, it must be the normal reaction. Normal reaction means it must be at 90 degrees to the ground. So the ground in normal reaction only, then against a rough wall. Because the wall is rough, then the resultant reaction, resultant is of friction and the normal reaction. The normal reaction is due to contact, then there's friction because it's rough. Then the resultant of these two is the resultant force, the resultant reaction on the wall. So which diagram shows the direction of the forces P, W, and R acting on the ladder as it slides? So W is the weight. So in all cases, the weight is downward, so we can't eliminate any using W. Then on the wall, on the ground, we must have only one force which is normal to the ground. So this one, we have only one force normal to the ground, one force normal to the ground. Now it means we eliminated D and C because the reaction there is not normal to the ground, yet the ground is smooth. So the force R must be perpendicular to the ground. It's only the normal reaction So we have eliminated C and D. Then we remain with A and B, and we have to look at the reaction, the resultant reaction at the wall. It can't be normal because there's a normal reaction force which makes 90 degrees, and there's a frictional force. Therefore, the force cannot be perpendicular, which makes this one also wrong. Because if it starts sliding, it slides downwards, there is no more reaction force upwards. I mean, there is friction force, this is friction, and there will be no more reaction force. The resultant must be somewhere there. This is the resultant. So this is normal reaction, friction on the wall, which gives us the resultant. So if it starts sliding downwards, there is friction upwards, and then there will be normal reaction. So the resultant P must not be normal. So the answer is going to be B. A toy parachute is dropped from a bridge and falls vertically through the air. The graph shows the distance traveled by the parachute against time. Which region of the graph shows when the parachute is at terminal velocity? Of course, terminal velocity means constant velocity. This means constant velocity. Since it is a distance against time, then the gradient equals to the velocity. The gradient will be velocity, and the gradient is constant at B. So the answer is going to be B. Here, the gradient is 0. Here at A, the gradient is increasing. Here at B, the gradient is constant. So the answer is going to be B. A lift in bracket elevator consists of a passenger car supported by a cable that runs over a light frictionless pulley to a counterbalance. The counterbalance falls as the passenger car rises. Okay, so the counterbalance falls. If it falls, there is a weight downwards. Remember, there is tension in the cable. There is tension which always points out from the weight or from the object. So there is tension here. Let's say the weight of this one is, I'm going to call the mass of this one small m. And I'm going to call the total mass of this one. So this is small m times g. That is the weight of this one. I'll call the weight of this one capital M times g. Okay, so it is falling in this direction, so the acceleration is in this direction, and it's the same. The acceleration this side is going to be upwards. So some masses are in the table. So the total mass here, the passenger car and the passenger 80, total mass here is going to be 600 kilograms. The mass of this one was, the counterbalance is 640 kilograms. What is the magnitude of the acceleration of the car when carrying just one passenger and when the pulley is free to rotate? Okay, so on the left-hand side, the resultant force F equals to mass times acceleration, which is going to be equal to the difference between these two, that is the weight, that is mg minus the tension T. I'll make some substitutions. The small mass is 640 times the acceleration equals to 640 times g minus the tension on that side. On this side, on this other side also, I'll use this other side for the passenger car with the person. The resultant force F is going to be equal to capital M times the mass, which is going to be equal to, because the motion is upwards, so the tension T is greater than mg. So this is going to be equal to capital T minus capital M times G. So it means capital M is 600 times the acceleration is the same, the tension minus 600, then times G. So this is going to be the second equation if this was my first equation. So I'm going to add the first equation to the second equation. So equation 1 plus equation 2. So when I add equation 1 plus equation 2, I'm going to have that 640A plus 600A equals to, the tension T disappears when you add the two equations, T cancels out. And then when you add the two equations, you have 640G plus negative 600G. So common factor is A. So when we add this, 640 plus 600, that's 1240A. So I have the 1240A equals to, when you subtract this, this is 40G, which is 40 times 9.81. So we are just going to divide. A is going to be equal to 40 times 9.81 divided by 1240. So let's check the calculator. 40 times 9.81 divided by 1240. So that is 0.316 meters per second squared, which is approximately 0.32 meters per second squared. So this means our answer is going to be B. A stationary ball of mass m is hit by a bat. The ball leaves the bat with a velocity v. The bat is in contact with the ball for a short time delta t. What is the average force of the bat on the ball? By definition of average force, or by definition of force, force is equal to the rate of change of momentum. Force is the rate of change of momentum. And of course, we know that momentum is equal to mass times velocity. Because it starts from rest, then it gets velocity v, then it means the change in momentum is simply going to be mass times the change in velocity, which is simply going to be m into v minus 0, which is mv. So the force, therefore, is going to be equal to the change in momentum, which is m times v divided by delta t. So this means the answer is going to be equal to B. A disk of mass m is moving across a horizontal frictionless surface with a constant velocity u. It collides with a stationary disk of mass 4m, so the disk is stationary. The diagram shows the view from above of the motion of the two disks before and after the collision. Okay, so this is the diagram. What is the initial velocity u of the disk of mass m? Okay. So first of all, I'm going to consider horizontal. I'm going to consider momentum in the vertical, and I find v. Then I consider momentum in the horizontal to be able to find u. By conservation of momentum in the vertical, we are conserving vertical momentum. Total momentum before collision in the vertical was 0 because the mass was moving horizontally. Total momentum after collision, of course, I have to resolve this in the vertical. If we resolve this to the vertical, this will be 4. Velocity will be 4 sine of 45. It will be upwards. And this one in the vertical, it will be v sine of 45, and it will be downwards. So total momentum in the vertical, remember momentum is mass times velocity. So in the vertical, one is upwards, so I'll just say capital M times 4 sine of 45. plus, the other one will be negative. So plus negative or plus minus 4m sine of 45. So when you solve this, it means 4m sine 45 is equal to 4m. No, this is 4m times v. There's a v here. The mass is 4m times v sine 45. So minus 4m times v sine 45. So it means 4m times v sine 45. This means v equals to, because m cancels out, the 4 also cancels out, sine 45 also cancels out, so v is equal to 1 meter per second. V is equal to 1 meter per second. If we consider vertical motion, v is 1 meter per second. Then let's consider horizontal momentum. I'm going to consider horizontal momentum from this side. Horizontal. Let's conserve horizontal momentum. Initially in the horizontal, 4m was at rest and capital M was moving. So the initial momentum was m times u plus 0. This should be equal to, after the collision, we have to resolve this in the horizontal. So for this one, the velocity is going to be 4 cos of 45. For this one at the bottom will also be 4 cos of 45. So this is going to be capital M times the velocity, which is 4 cos of 45, plus the other one is going to be 4m. No, the velocity here is v, not 4. So this is going to be m times 4 cos 45, then plus v, which v is 1, of course. Let me first write the mass here. So this is plus, the mass is 4m times v cos of 45. But remember, v is 1. M has cancelled, so u is going to be equal to 4 cos 45 plus 4 times 1 cos of 45. So u is going to be 2 times 4 cos of 45, or it is 8 cos of 45. So if I try to check the calculator, 8 cos 45, 8 cos 45 is giving us 5.66, or 5.7 meters per second. So the answer is going to be D. An object is dropped from rest on the earth from a height of 2 meters. The same object is dropped from rest on the moon from twice the height. The acceleration of free fall on the moon is approximately 16%. So acceleration on the moon is 16%. That is 16 over 100 times the acceleration on the earth. So let's say acceleration on earth is going to be g. The acceleration on the moon is going to be 16 over 100 times g. Okay, or which is 0.16 g. Assume that there are no resistive forces acting on the object. So the accelerations are going to be constant. What is the ratio speed of the object just before hitting the surface on the earth over speed of the object just before hitting the surface of the moon? Because there are no resistive forces, the accelerations are constant, so equations of motion can apply. Therefore, I'm going to just use v squared equals to u squared plus 2as. So if I try to find the v on the earth, the speed with which it hits the ground, v on earth squared is going to be equal to because they were released from rest, so U will be 0, so it will be 2 times G times the height is 2. Okay, that is G on Earth. I mean V squared on Earth. Then when I consider V squared on the moon, then this is going to be equal to 2 times G acceleration on the moon, which is 0.16 G times, because it's dropped from a height which is twice the height of the Earth, so this is going to be 2 times 2, twice the height of the Earth. The height of the Earth was 2. The height of the moon is going to be therefore 2 times 2, which is 4. So this means this is going to be the second equation. So I'm just going to solve these two equations. So I have that V on Earth squared is equal to 4G, and I have that V squared for the moon equals to, this is 2 times 2 times 2 times 0.16. That is 1.28. 1.28 times G. So I want the ratio speed for Earth over speed for the moon. So the ratio is going to be, of course, I will get the square root. So the ratio is going to be the square root of 4G divided by 1.28 times G, and the G cancels out. So I'll just say 4 divided by 1.28, then under the square root. So that's 1.768. Oh, it is approximately 1.8. So the ratio is 1.8, which makes the answer to be A. The graph shows how velocity v varies with time t for a bungee jumper. So this is velocity against time. At which point is the bungee jumper momentarily at rest? And at which point does she have zero acceleration? So momentarily at rest means v goes to 0. So v is 0 only at r. Then at which point does she have zero acceleration? Remember, this is a graph of velocity against time. The gradient equals to the acceleration. And this is equal to 0 at, the gradient is 0 at point Q, because this, if I draw a tangent here, it will be a horizontal line, which means the gradient is 0 at point Q, because the gradient of a horizontal line is 0. So the gradient is the acceleration, which is equal to 0 at point Q. So the answer here is automatically 0 velocity at r. So here it is 0 velocity, momentarily at rest, and then 0 gradient at Q. So the answer is going to be C. A solid sphere which is less dense than water is held completely immersed in water a few meters below the surface. Because it is less dense, we know that when it is released, it is going to raise upwards. The sphere is released. Immediately after release, the sphere rises. Note that the density of water is uniform. Which law describes the changes in the magnitude of the upthrust on the sphere and the resultant force on the sphere as it raises? So if I'll just sketch this for clarity, let's say this is the water and the sphere is held here, and let's say this is the surface. When it is released, the forces which are acting, we have the weight downwards. Because it is going to move up, of course, the upthrust force is always acting upwards. This is upthrust. And then when it moves upwards, the drag force moves down, acts downwards. So this is the drag. The drag will be downwards. So this is the weight. This is the upthrust. So, of course, if it is fully submerged, then the upthrust remains constant, because the upthrust depends on the difference between the pressure on the top and the pressure on the bottom, which is also the same as the upthrust is equal to the cross-sectional area times the difference in pressure. The difference in the pressure depends on the difference in the height on the top and the bottom, or it will now depend on the difference on the pressure of the top and that of the bottom, and it's going to remain constant if it is fully submerged. So the upthrust remains constant, but then what happens to the resultant force? As it moves upwards, the drag force decreases. So the drag, actually, as it moves upwards, we know that D depends on the speed. D depends on the speed, so D is going to increase. The resultant force, because it is moving upwards, the resultant force is going to be the upthrust minus the force acting downwards, which are the weight plus the drag force. And upthrust is constant, the weight is constant, but the drag force increases because drag depends on the speed. And the speed is going to increase as it raises because it's lighter. So the speed increases, so the drag increases. So drag depends on the speed, and the speed increases. So if the drag increases, then it means this bracket here is going to be bigger. The difference is going to be smaller. So speed increases, drag depends on the speed, speed increases. So the resultant force therefore decreases. So the upthrust remains constant, so we ignore C and D. Then we have said the resultant force on the sphere decreases, so the answer is going to be automatically A. A uniform bar of weight 200 newtons and length 4 meters is freely hinged on the wall at one end. The bar is horizontal and is held in equilibrium by a cable attached at a distance of 0.5 meters from the other end. The cable is at an angle of 35 degrees to the horizontal. What is the tension in the cable? So the easiest way to do this is always because it's uniform, its weight acts at the midpoint. So the weight should be somewhere here. It is 200 newtons, so I'll put here 200 newtons. That's the weight of the beam or the weight of the bar. And I'm going to resolve the tension in the vertical so that it's easier for me to find the vertical distance. So the tension resolved to the vertical will be T sine of 35. And T sine 35 is going to cause a moment in that direction, which is clockwise. And the weight of the bar is going to cause a moment in that direction, which is anti-clockwise. So for equilibrium, the sum of clockwise moments equals the sum of anti-clockwise moments. The sum of clockwise moments equals to the sum of anti-clockwise moments. So I will say T sine of 35, and the perpendicular distance is going to be 4 minus 0. So this distance here is going to be 4 minus 0.5, which is 3.5. So this is times 3.5 should be called the sum of anticlockwise moments. So this perpendicular distance is going to be half of 4, which is 2.0 meters. So this is going to be 3.5. So this is going to be 200 times 2.0. So what is T? T is going to be 200 times 2.0 divided by 3.5 sine of 35. So 200 times 2 divided by 3.5 sine of 35. So that's 199, which is approximately 200. So the answer here is going to be C, because this is approximately 200. The diagrams all show a pair of equal forces acting on a meter ruler. Which diagram shows forces that provide a couple and zero resultant force? A couple, these are supposed to be two equal forces, They should be in opposite directions. They should be in opposite directions, and they should give a resultant zero force. But the torque resultant moment is not zero. Moment is not equal to zero. So they should have those properties. There should be two equal forces which are in opposite directions. So it means A is out. They are not in opposite directions. Then D is also going to be out because these two forces are not in opposite directions. So these are not equal. When we say opposite directions, they should even be parallel to each other. So we have to look at B and C. Remember, for the couple, the lines of action never meet. Their lines of action never meet. So it means the C is also out because C, the lines of action are meeting. And by the way, even in D, when you extend the line of action of this force, it will always meet this one. So yet for a couple, the lines of action of the two forces should never meet. Therefore, it means our answer is going to be B. The lines of action of these two forces never meet. These two forces are equal and opposite direction, so they satisfy this condition, their resultant will be zero. The moment is not zero because they are going to cause rotation in this direction here. So these ones cause rotation. In other words, the moment is not zero because a couple normally causes a rotation in one particular direction. A ball of mass m is thrown up to height h in air with an initial velocity v, as shown. Air resistance is negligible, so the equations of motion can be employed. The acceleration of free fall is g. What is the total work done by the gravitational force on the ball during its flight from P to Q? Remember, work done is equal to force times the displacement in the direction of the force. If we consider the vertical displacement, because the gravitational force acts in the vertical, so the vertical displacement equals to zero. Vertical displacement equals to zero, which means the work done is automatically going to be zero because the work done by the gravitational force must be the vertical gravitational force and the vertical displacement. From P to Q, the vertical displacement is zero, so the answer is automatically going to be A because P and Q are on the same level, so the displacement is zero. Therefore, the work done is going to be zero. A spring of spring constant 30 newtons per meter is suspended vertically from its top. The spring obeys Hooke's law. Initially, the spring is not compressed and not stretched. So it's not compressed, neither is it stretched. Okay. A mass of 0.5 kilograms is attached to the bottom of the spring. The mass is released from rest and falls. Remember, it was not compressed nor stretched, but then the mass is released from rest and then it falls. Frictional forces are negligible. In the motion that follows, what is the maximum extension of the spring? Because it was not compressed and not stretched, then the maximum extension is going to be 2 times the normal extension. So let's first find the normal extension from Hooke's law. F is equal to K times extension. So the normal extension is going to be equal to the force divided by the constant K. The force is going to be the weight, which is mg, divided by K. M is 0.50 times G, which is 9.81. Then divide this by K, which is given as 30. So the normal extension is going to be equal to 0.5 times 9.81 divided by 30. So that is 0.16. That's the normal extension 0.1635 meters. But because it was not initially compressed and not stretched, then therefore the maximum extension is going to be twice this. So maximum extension is going to be 2 times 0.1635. So I will multiply this by 2. So 0.327, which is going to make a D as our answer, approximately 0.33 meters. A wire has original length L and cross-sectional area A. A tensile force F is applied to the wire, which causes it to have an extension X. The wire obeys Hooke's law. So if the wire obeys Hooke's law, then we know that Young modulus is stress over strain, which means stress is force over area and strain is extension of original length. So when you divide, Young modulus is going to be the force over the area times, when you get the reciprocal, it will be original length divided by the extension. Divided by the extension. I'll use E for extension. What is an expression for the Young modulus of the material from which the wire is made? So stress times X over L. So this is out because stress is force over area, then times extension over original length. This is the same as stress times extension. X is the extension and L is the original length. Stress times extension, that is not Young modulus. This one is the same as stress times strain. Stress times strain is not Young modulus. Force over area, that is stress. This is stress over strain. Stress over strain, that is Young modulus. This one alone is stress divided by strain. So the answer is going to be B. That's the Young modulus, because we know that Young modulus is stress divided by strain. Stress is force over area divided by strain. So the answer is B. A wire is stretched by a gradually increasing force. Gradually increasing. The force extension graph for the wire is shown. Which statement must be correct? Point Q is the elastic limit. The elastic limit is normally slightly beyond where the straight line is. This is most likely going to be the elastic limit. R is most likely going to be the elastic limit, slightly beyond. So this one is not true. Point R is the limit of proportionality. R is the elastic limit. The limit of proportionality is most likely going to be P. This is the limit. Q is most likely going to be the limit of proportionality. So this means this statement is also not correct. The area under the graph from P to S is the elastic potential energy in the wire. The elastic potential energy is only obtained from that is that energy which can only be returned, and this is only for the straight line part. So this one is given by the part where Hooke's law is obeyed. In other words, the straight line part. So it means this statement is also not correct. PS is not the elastic potential energy. Elastic potential energy will only be the area under P to Q. The area under the graph from P to S is the work done in stretching the material, so this must be correct. Total work done in stretching the material is the area under the whole graph. So that is correct. If it is elastic potential energy, it is only for the straight line part. A spring has an unstretched length of 0.30 meters and a spring constant of 400 newtons per meter. An object is suspended from the spring and the spring is deformed within its limit of proportionality. The new length of the spring is 0.5 meters. What is the elastic potential energy of in the spring? Okay, so of course we know that elastic potential energy is equal to a half Fx, or it's a half Kx squared. Since I have K, I have the unstretched length, I have the new length, then the extension is going to be 0.5 minus 0.3. So I'll just substitute this to be a half times 400 times 0.5 square 0.5. Of course, x is the extension, which is the difference. So it is 0.5 minus 0.3, and this is squared. So this is going to be equal to 0.5 times 400 times 0.2. Sorry, 0.5 times 400 times 0.2 squared, which is 8. So the answer is going to be A. A wire consists of a 3-meter length of metal X joined to a 1.0 meter length of metal Y. The cross-sectional area of the wire is uniform. Okay, so this is X and this is Y. A load hung from the wire causes metal X to extend by 1.5. So this is extending by 1.5 meters, and Y to extend by 1 millimeter. This is by 1.5 millimeters. This is by 1 millimeter. The same load is then hung from a second wire of the same cross-sectional area. So let me have a second wire here. So let the load be F. Same cross-sectional area. So area is the same. Area here is A. Area here is A. Consisting of 1 meter length of X. So now X is 1 meter. That is X. And 3 meter length Y. So now Y is the one which is 3 meters. So this is Y. Both wires are extended within their limits of proportionality. What is the total extension of the second wire? So let's say initially, I'm just going to use the idea of Young modulus to find these extensions. So for the first case, we know that Young modulus equals to the force over area times original length over the extension. And we know that force over extension is equal to a constant K. If they're extended within their limits of proportionality, F over A extension is equal to a constant K. So it means Young modulus is going to be a constant K times L divided by the area A. Okay, so let me start with wire X. So Young modulus of wire X is going to be equal to the constant, the constant of X, the constant of X times the length of X, which is 3 times the 3 meters, divided by the area sorry, I don't need to use K. I'll just use, because the extension may not be the same. No, I have to change this. I'll change my constant. Let it not be spring constant. So Young modulus is equal to force over area times original length over extension. We know that force, the same load is applied, and the cross-sectional area of the wires is the same. Okay, so this is F over A is going to be constant, which I'm going to call K. So let's say K equals to F over A. So E for X is going to be K for X times L for X, which is 3 meters, divided by the extension for X, which is going to be E for X. That is for on this side. On the other side, so this is also going to be, I'm looking at the same wire the other side, because Young modulus depends on the material. It is the same for X, whether it is a shorter X or a longer X. So this is going to be the same as K, that is the force over area, is going to remain the same. So it will be K for X times the length, this side is 1 meter, over the extension for X, which is not known. But this, the first one was known. For the first wire, it was 1.5. For the second wire of X, it wasn't known. So K is going to cancel out, meters cancels out. So extension for X is going to be equal to 1.5 millimeters divided by 3, which is equal to 0.5 millimeters. So the extension for the new wire is 0.5 millimeters. I'm going to repeat the same for the wire Y. Young modulus of wire Y is also going to be K for the wire Y. K for the wire Y times the original length for the wire Y, which was 1.0 meters, divided by the extension of the first wire Y, which is 1.0 millimeters. This should be also the same for the second wire, which is going to be K for wire Y, times the length, which is 3 meters, divided by the extension for wire Y, which is not known. I'll just call it EY. So meters has cancelled, the constant has cancelled. So it means E for wire Y is going to be equal to 3 times 1.0 millimeters, which is 3.0 millimeters. So we have seen that extension for this one is 0.5 millimeters, and extension for this one is 3.0 millimeters. So total extension is going to be 0.5 plus 3.0, which is 3.5 millimeters. So the answer is going to be B. The graph shows the variation of the displacement with the distance for a progressive wave at one instant in time. The period of the wave is 91 milliseconds. What can be determined about the wave? It has a velocity of 0.44 meters per second and a frequency of 11 hertz. We can check the velocity. The velocity is going to be equal to lambda times f, which is the same as lambda divided by the period. And this is the same as the wavelength from the graph. The wavelength is, I think the wavelength is 4 meters. This is the wavelength, which is going to be 4 it's actually 4 centimeters. That is 4 times 10 to the power of minus 2. So lambda is 4 centimeters. Divided by the period is 91 times 10 to the power of minus 3. So 4 exponent minus 2 divided by 91 exponent minus 3. So that is 0.44. So the speed is correct, 0.44 meters per second. But the frequency, of course, the frequency is just 1 over. Frequency equals to 1 over period. That is 1 over 91 times 10 to the power of minus 3. 1 divided by 91 exponent minus 3. So that is 10.989, which is approximately 11. So the answer is A. Without even checking the rest, the answer is A. Which group of electromagnetic waves is arranged in order from the shortest wavelength to the longest? So remember the general mnemonic: Reed's mother is visiting Uncle Xavier's garden. So this is order of wavelength decreasing wavelength. So let's see. Radio waves, visible light. Which one has they said from shortest wavelength to longest. Radio waves have the longest wavelength. These ones are the longest. And this is shortest. From shortest to longest. So radio waves cannot be the first. So visible microwaves have a longer wavelength than visible. So this is wrong. Visible ultraviolet, that is true. Visible light has a longer wavelength than ultraviolet and also than X-rays. So the answer here is automatically from shortest wavelength to longest. Okay. Shortest to longest. So visible has a longer wavelength than ultraviolet. So this is also not correct because we are starting from shortest. So it would have been X ultraviolet, then visible. X-rays have a shorter wavelength than infrared. Infrared have a shorter wavelength than microwave. So the answer is D. A wave has a frequency of 5 gigahertz. What is the period of the wave? So period is equal to 1 over f, which is 1 divided by 5 times 10 to the power of 9. That is giga. 1 divided by 5 exponent 9. So that is 2 times 10 to the power of minus 10 seconds. And this is the same as, I'll check the first one, changing this to pico. 2 times 10 to the power of minus 10 divided by 10 to the power of minus 12 to change it to picoseconds. And I think this is 200 picoseconds. So the answer is A. Three statements about two progressive waves are listed. They have the same frequency, they have the same amplitude. The waves are emitted with a constant phase difference. Which statement must be correct for the two waves to be coherent? Of course, for coherent waves, they must maintain a constant phase difference. So your answer should always have 3. So it means B is not going to be correct. We have A, C, and D because coherent means maintaining a constant phase difference. The only way we can maintain a constant phase difference is if the waves have the same frequency. So they should have the same frequency in order to maintain a constant phase difference. Therefore, the answer is going to be 1 and 3. So the answer is going to be option C. Waves P and Q have the same amplitude. The waves meet in phase at point X and interfere to give a resultant wave with intensity I. The amplitude of wave P is doubled. Wave P amplitude is doubled. What is the new intensity of the resultant wave at X in terms of I? So we know the relationship between intensity and amplitude. We know that intensity equals to a constant times the amplitude squared. So for the first case, they had the same amplitude. So and the intensity was I. So I is equal to a constant K. The amplitude of P was A. The amplitude of Q was also A, and this was squared. So it means I is going to be equal to K, because K into 2A, but this is squared, so I was equal to 4K A squared. That's number one. Number two, now the amplitude of P is doubled. The amplitude of A has remained the same. So the new intensity I will call it I2. I2 is going to be equal to a constant K into A plus 2A, because 1 is doubled, then this is squared. So this I2 is going to be equal to, because this is 3, so it becomes 9K A squared. So I'm going to divide I2 divided by I. This is going to be 9K A squared divided by K 4K A squared. So I2 is going to be equal to 9 over 4 times I. So 9 divided by 4. That is 2.25, which is 2.3. So the answer is going to be C. Radio waves can be polarized, but sound waves cannot be polarized. Which statement gives the reason for this? Radio waves are generally of a high frequency than sound waves. Radio waves have a high wavelength, but they have a lower uh, frequency, but then it could be it could be higher than that of sound, but that does not explain polarization. So this statement is not true. The transverse nature of radio waves is what explains because polarization is evidence that the wave is transverse. All waves, transverse waves, undergo polarization. So radio waves are transverse, but sound waves are longitudinal. So the answer is B. Light of wavelength lambda is incident normally on a radioactive grating with a total number of n lines in width W. A second order maximum is observed at an angle of diffraction theta. What is n? So from the diffraction equation, n lambda equals to d sine of theta, and n is 2. So 2 times lambda equals to d sine of theta. But we know that d equals to the number of lines, a total number of lines, of n lines in width W. So in the width W, we have n lines. So D is going to be the width divided by the number of lines. So twice lambda is going to be the width divided by the number of lines, sine of theta. So capital N is going to be W sine of theta divided by twice lambda. So the answer here is going to be option C. Kirchhoff's second law is a consequence of a basic principle. Kirchhoff's law is, of course, dealing with the sum of voltages. The sum of EMFs is equal to the sum of PDs, and EMF and PD, that is energy. So what is this principle? So this is the principle of conservation of energy. The charge flowing in an electric circuit is conserved. The energy in an electric circuit is conserved. So the answer is B. The diagram shows a circuit with a light-dependent resistor, that's the LDR. The ammeter reads 0 current. What is the resistance of the LDR? So if the ammeter reads 0 current, the PD across this part is the same PD across this part. The PD across this section is the same PD across this section. So let's first find that PD. So the PD across 10 kilo ohms is the same as 10. I'm using the potential divider formula. So it will be 10 over 10 plus 30, then times the voltage supply, which is 12. And this speed is 10 over 40 times 12, which is 3 volts. The PD across 10 kilo ohms is the same as the PD across the 6 kilo ohms, which is also going to be 3 volts. So it means the PD across the LDR, we shall just subtract. The PD across the LDR is therefore going to be 12 minus 3, which is 9 volts. if this is 3 volts, this should be 9 volts. So now I know the PD across the LDR. I can find the current through the 6 kilo ohm resistor, which is the same current through the LDR. So the current in the 6 kilo ohm resistor is of course V over R, which is going to be 3 divided by 6. And I think this is 0. This is 6,000. 3 divided by 6,000, and I think this is, let me check, 3 divided by 6,000, 5 times 10 to the power of minus 4. That is the current in the 6 kilo ohm. Because the current here is 0, I here is 0, so it means the same current. The current in the 6 kilo ohm resistor is the same current in the LDR. Therefore, now our resistance of the LDR is going to be V, which is 9 volts, divided by the current, which is 5 times 10 to the power of minus 4. So 9 divided by the answer, that is 18,000 ohms, which is the same as 18 kilo ohms. So this makes the answer to be B. A torch uses 3 lamps connected in parallel and is powered by a cell of EMF 3 volts and a negligible internal resistance. Each lamp dissipates 0.60 watts of power. What is the current in the cell? If you want to sketch this, you have 3 lamps, number 1, number 2, number 3, and they're in parallel. And they are connected across a power supply of 3 volts. So it means the PD across each lamp is 3 volts. Okay? But each lamp has a power of 0.6 watts. So let's find the current in one lamp. I in one lamp. So I'll get it from power equals to I times V. So the current in one lamp is going to be the power, which is 0.60, divided by V, which is 3. The current in one lamp is 0.2 amperes. But if we have 0.2 amperes, let's say here, 0.2 amperes plus 0.2 amperes plus 0.2 amperes, the current combines here to give a total current. So I in the cell is going to be 0.2 times 3, which is 0.6 amperes. So the answer here is going to be C. A cell of internal resistance is connected to a light-dependent resistor, a fixed resistor, and a voltmeter, as shown. The voltmeter reading increases. The voltmeter reading increases, which means the PD across the fixed resistor increases. So I'll call the PD across here, I'll call this one resistance of LDR, I'll call this one fixed resistor R, and this is going to be the PD across, this is going to be PD across R. Whenever I talk about the PD of the light dependent resistor, I will say PD across RL. So the voltmeter reading increases. Which quantity decreases as the voltmeter reading increases? So if the voltmeter reading increases, then it means the PD across the fixed resistor has increased. And if that increases, it means the PD across the LDR must have decreased. And if the PD across the LDR has decreased from V equals to IR, it means the resistance of the LDR must have decreased. The resistance of the LDR must have decreased for the PD across the LDR to decrease. And if the resistance of the LDR has decreased, How does the resistance of the LDR decrease? That's when the light intensity increases. So if resistance of the LDR decreased, then light intensity must have increased because they are inversely proportional. So the light intensity must have decreased. What has happened to the total current? Because the resistance of the LDR has decreased, then the total current, I total, must have increased. So total current must have increased because total resistance must have decreased. So which quantity decreases as the voltmeter reading increases? 1. The charge moving through the cell per unit time. The charge moving through the cell per unit time, that is the current. We have said the total current increases, so this statement is not correct. The energy transferred to the fixed resistor per unit charge. The energy per unit charge, that is the PD, that is PD across R, which has actually increased. So this statement is a contradiction. The intensity of the light incident on the LDR. Which quantity decreases? We have seen that the light intensity increases, so this one is also not true. Here, light intensity increases. The terminal PD across the cell. The terminal PD across the cell decreases. So the answer is most likely going to be D. The answer is most likely going to be D. The terminal PD across the cell has decreased. Which quantity decreases as the voltmeter reading increases? So if the terminal PD has decreased, because the terminal PD is going to be equal to the total resistance outside, resistance, which is R plus RL, then times the current, because the resistance of the LDR decreases, and because the current increases, I increases, it means the lost volts increases. And remember, because the EMF remains constant, terminal PD is also equal to EMF minus the lost volts. When the lost volts increase, this one increases, so the terminal PD has decreased. So the answer is D. The circuit shown contains a cell with a negligible internal resistance. The energy transferred per unit charge in driving the charge around the complete circuit is E. Okay, the energy transferred is E. The potential difference across X is V. So in this case, E is going to be the same as V if there is no internal resistance. The cell is then replaced with a different cell of the same EMF that has significant internal resistance. So this time, the same EMF E is going to be equal to the, because it has some internal resistance, it is going to be equal to the terminal PD, let me call it V1, plus the lost volts. What is the effect on E and V of replacing the cell? Of course, because it has the same EMF, this one, the energy required to move a charge, charge around the complete circuit is also the EMF. So the EMF has no effect. Therefore, we eliminate A and B. There is no effect on E. But then what happens to the V? So V1 is going to be EMF minus the lost volts in the second case. Because there's internal resistance in the second cell, the value of V1 is going to be less than V. So V1 is going to be less than V. So V1 decreases. So the answer is going to be C. V1 is less than V. So we say V decreases. Okay. In the circuit shown, the batteries are identical and all have negligible internal resistance. All of the resistors have the same resistance. The diodes have zero resistance when conducting and infinite resistance when not conducting. In which circuit is the current in the battery greatest? Let's first check if the diodes are all conducting. So the diodes conduct in one direction. So current is flowing in this direction. So this can conduct, this can conduct. B, both diodes are conducting because they're in the right direction of current. Then C, this diode is not conducting because current is flowing like this. It comes like this. It can't continue here. So this one is out. In which circuit is the current in the battery greatest? If the diode is not conducting, then in the second case also, this diode will not be conducting. So the question is, in which circuit is the current in the battery greatest? In the circuits, the batteries are identical and all have negligible internal resistance. All of the resistors have the same resistance. The diodes have zero resistance when conducting and infinite resistance when not conducting. So here, when the diode is not conducting, the resistance is equal to infinity. The resistance equals to infinity. The resistance here is infinity for the diode when it is not conducting, and it is zero when it is conducting. So in which circuit is the current in the battery greatest? So this diode is conducting and this is conducting, so their resistance here is going to be zero. Therefore, total resistance here is going to be lower. Total resistance here is going to be lower because these resistors are in parallel, so the answer is going to be A. It can't be B because the resistors are in series. Total resistance is higher than before, so here the current is low because this one has a higher resistance, because resistors are in series. So lower current. But these ones are in parallel. Because these ones are in parallel, then the resistance is low. So low resistance and higher current. A potentiometer circuit is used to determine the EMF E of the cell. The circuit induces a second cell. Circuit includes a second cell of EMF 1.5, an internal resistance of 0.5 that is connected to a uniform resistance wire XY as shown. Okay. The resistance wire XY has length 0.96 meters and a resistance of 0.5 ohms. The movable connection Z is moved along wire XY. The galvanometer reading is 0 when length XY is 0.64 meters. What is the value of the EMF E? Okay, so first of all, I want us to note that the PD across XZ, when there is a balance, is going to be the same as the EMF E. Our task is going to be just to find the PD across XZ. The PD across XY is going to be equal to the EMF minus the lost volts, which is going to be 1.5 minus the current times the internal resistance. So let's first find the current. The current is going to be equal to the EMF, which is 1.5, divided by the current is going to be the EMF, which is 1.5. Okay, so the current flowing through IX, the current flowing through XY is the same current flowing through the battery. So the PD across XY so this is going to be V. I'm just going to use V or EMF over total resistance. That is the current. The current is going to be the EMF over total resistance. The EMF is 1.5. Total resistance is the internal resistor, which is 0.5, plus the resistance of the wire X, which is 0.5, which is 1.5 divided by 1. So the current is 1.5 amperes. The current here is 1.5 amperes. It is the same current here. Okay, so it means I can now find the lost volts. The lost volts is the current, which is 1.5 times internal resistance, which is 0.5. So the lost volts is going to be, I think this is 0.75 volts. So it means the PD across XY is going to be equal to 1.5 minus the lost volts, which is 0.75. So the PD across XY is 1.5 minus 0.75. That is the EMF minus the lost volts. And this gives us, I think this is also 0.75 volts. So the PD across XZ can now be found. How? Now that I know the PD across XY, I just get the ratio PD across XZ over PD across XY is directly proportional to the length. So this is going to be the balance length was 0.64 meters divided by 0.96 meters. So the PD across XZ is going to be 0.64 divided by 0.96 times the PD across XY, which is 0.75, which gives us 0.64 divided by 0.96, then times 0.75, which is a half. So that is 0.5. Remember I said the PD across XZ is the same as the EMF E, not the EMF of the driver cell. So the answer is 0.5, which makes the answer to be A. Which particle is not fundamental? Fundamental particles are not made out of anything else. They are the simplest. Quarks are fundamental particles. Electrons are not broken down any further, so they are fundamental particles. Neutrinos are not broken down any further, so they are fundamental particles. But the neutron is not a fundamental particle because this one is made up of 3 quarks. In fact, it's made up of up, down, down. So it is not fundamental because it is made up of quarks. The isotope fluorine 18 undergoes beta plus decay to form a stable isotope. So fluorine F189 is undergoing beta plus, which is 0,1 decay to form a stable isotope, which isotope is going to be, let's say, X. So this will be 18 and this will be 8. Of course, whenever we have a beta plus decay, this is normally accompanied by a neutrino. So how many neutrons are there in a nucleus of the stable isotope? So the nucleon number is 18, the proton number is 8. So the number of neutrons is going to be 18 minus 8, which is equal to 10. Nucleon number minus proton number, which is equal to 10. So the answer is going to be D. And lastly, which statement is correct? A baryon is a hadron, which is true. Consists of 2 quarks. Baryons are made up of 3 quarks. A meson is a hadron, which is true. Consists of 3 quarks, which is not true. So a meson is made up of a quark plus an antiquark. An electron is a fundamental particle, which is true, and is also a lepton, which is also true. An electron is fundamental, it can't be broken down, and it is also a lepton, so the answer is going to be C. Yeah, I took a lot of time because I tried to show the working, and it takes a lot of time. Otherwise, I would have just read some questions and just highlighted the answers. So thank you for watching. Until next time, see you in the next paper. Bye bye.